Hello, everyone, and welcome to today's webinar on analyses of modified glass surfaces and thin coatings on glass. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted. However, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. Charles McGee, Chief Scientist at EAG Laboratories, will be answering some of the questions during the presentation, and we will also collect these and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce Tamel Buyuk-Lamanli, Vice President of Technology and Innovation at EAG Laboratories.
Good morning, good afternoon, and good evening. Welcome to our webinar. First, a little bit about me. I've been in the surface analysis field for over 35 years, which started with my graduate studies at University of Florida Materials Science. And since my start at EAG in 1994, roughly about 26 years ago, my focus has been on SIMS, and I participated in innovation of new SIMS methods over the years. Today, I will be showing you a few of those methods we develop being applied to glass surfaces and the coatings on glass. Also, a brief introduction to EAG. All the dots you see on the screen represents the EAG laboratories and their locations. As you may see, we have presence over 20 locations in 4 continents, and we have staff over 600 and scientists with highly educated and experienced people. We serve over 4,000 clients per year who are located in 50 different countries. This chart shows all the techniques available at EAG. We call it the SMART chart. It stands for Smart Spectroscopy and Microscopy Analytical Resolution Tool. The vertical axis of this chart represents the concentration detection limits in atoms per cubic centimeter or in atom percent. The bottom axis is representing the analytical spot size or the feature size that each technique can analyze. The colors of the circles represent the type of information extracted from the materials, such as the blue techniques are representing the elemental information, whereas the orange circles are providing molecular information as described in this legend. You can download this map from our website and have a better understanding of all these techniques and what their capabilities are. The techniques outside this chart are for imaging, where you don't get any compositional information, but getting morphological information from the materials. Again, they are plotted with respect to this feature size. They can measure with electron microscopy, transmission electron microscopy, having the highest resolution to resolve monolayers or atoms in a material. Whereas on the vertical axis, these are bulk techniques, and these techniques will not give you any in-depth distribution values. It gives you an average concentration and a volume of material. And again, the extent of these curves shows the detection limit of each of these individual techniques. Dynamic SIMS occupies the center of that chart. We're going to be looking at a lot of dynamic SIMS analyses, and as you can see in all the techniques we have, it has the lowest detection limit capability and a very high dynamic range. In other words, it can quantify elements at parts per trillion to atom percent level, provided that the analysis is set up properly. In parallel to that, just like we do all of this every day at EAG, we're going to look at complementary techniques to really make sense of the SIMS data we're getting using Auger electron spectroscopy and also scanning transmission electron microscopy. So let's start with the SIMS. This is a basic schematic of a SIMS instrument where the primary ion beam is hitting the area of interest, causing the material sputtered off. These particles coming off the surface are going to be either charging positive ions or negative ions or neutrals. We apply an electric field to extract the ions of particular polarity into a mass spectrometer or a mass filter, which is controlled by a computer to allow only a specific mass to be detected at our detector. When we scan the masses in this mass spectrometer, we end up getting a mass spectra, or we can fix it to a certain mass and then map the area that ion source is sputtering and get an image of that area for that particular mass or other masses. We also get an in-depth distribution of a given mass or masses. As we're drilling into the material, we collect these signals in a sequential manner and end up with a depth profile. For dynamic SIMS technique, this is the most commonly used method of extracting information from your sample. Depending on what type of analysis you need to use, we choose one or the two ion sources. We can only detect one particular ion coming into our material. So we set up the instrument or the detection based on the elements that are needed to be measured. One challenge with the SIMS is the quantification of the intensities that are coming out, and it's an empirical technique, and it requires reference materials, and these SIMS standards or the reference materials have to have the same species in the same matrix of the unknowns for it to be relevant. And these standards need to be analyzed under the same analytical conditions of the unknowns we are measuring so that we can apply the calibration factors onto the unknowns reliably. Most often, the standards are generated by ion implantation into materials that we're going to measure. And over the years, we have come to know that this type of standard generation gives us an accuracy of roughly about plus or minus 15%, in some cases a little better. There's one other benefit to ion implantation standards, and I will touch on that in the upcoming slides, which is to look at the shape of the ion implants to really work out on any artifacts during the measurements and we calibrate the machine accordingly. So for insulating materials, the analysis gets a little more complex in that the charge buildup on the sample doesn't allow us to extract the ions consistently into our detecting system. So almost always we use a low energy electron beam in the vicinity of the crater that the ion beam is hitting to neutralize these charge built up, so we can essentially collect the ions coming off the surface with little impact of the charge built up in the material. This is particularly important when we're doing alkali ion or impurity measurements in bulk insulating samples, and I will show examples of how this can go really wrong. Why is alkali contamination is important in materials? In semiconductor world, the alkali contamination in dielectric causes leakage or shifts in breakdown voltages. Alkali contamination in transparent conductive oxides, indium tin oxide, causes shift in conductivity, just like in the dielectrics in semiconductors. They also often, if they're high enough concentration, affect the transparency of these films, and the source obviously needed to be known for determining the source of the contamination. So it becomes very important that the correct distribution of these mobile alkali elements are measured so that you can pinpoint where these contaminations might be coming from or their behavior. we have been doing these kinds of analyses for semiconductors for a long time. Now, we took that knowledge and applied them over the 20 plus years onto glass surfaces to look for alkali composition modification or alkali contamination coming from the substrate into the thin films, which I'm going to be showing today. So first, I want to impress upon you the challenges of doing alkali measurement in a bulk insulating. This is a profile or series of profiles on a fractured surface of a float glass. In other words, we break the glass, we look at the cross section, which represents the bulk of the glass, and if you were to profile for sodium, you should get a flat profile. But depending on the charge compensation you use, you may get very different profiles. As you can see, there are 4 different shapes of this, and all you're doing is changing the conditions of your electron beam. Ultimately, you're looking for this flat profile that represents the true distribution of the sodium in a cross section of the sodium. We jokingly say in the lab that you can dial any profile you want by changing the electron beam, which obviously is not desirable when you're trying to do a failure analysis of a bulk insulator or having a good understanding of where the sodium is in a bulk glass. But these conditions cannot be easily reproduced the next day. Every time you have to do this analysis, you have to go through this kind of an exercise to make sure you're not moving the sodium. As you can imagine, this is kind of painful to do if you're assigned to do the alkali analyses and insulating in bulk glasses. The sim scientists are usually not very happy about it because it's very challenging. You could be spending hours to get the perfect compensation. So let's look at how we can fix this thing. These are a series of alkali implants into conducting tin oxide, and the shapes of these profiles, ion implantation, done by ion implantation, can be checked against the theoretical distribution of these elements. They're well designed to these simulation programs can really get the true distribution of these ions into the matters that these implants are made. In a conducting film, we don't see any change of these distributions. So that tells us that even this is an oxide, because it's conducting, we don't have any mobility of these ions under the condition. But when we do the same measurement with the same sodium implant made into an SiO2, which is deposited on a conducting silicon substrate, depending on what electron charge compensation condition you use, you can actually drive the sodium profile. As you can see, it has nothing like a Gaussian shape we've seen in the conducting film. And we're driving all that sodium to the interface where the sputtering front reaches to conductivity, and the migration of the sodium stops. It can be so bad that most of the dose of that implanted sodium may end up at the epi-substrate interface. Obviously, this is not desirable, and these are the kind of reference materials we use, not just for calibration purposes, but to set up our instrument to prevent or minimize the migration of these mobile ions. I'll give you another example, and this time it's lithium. Lithium implanted into an SiO2 film that's sitting on a conducting silicon substrate. And this is the distribution that we get when the electron beam is not perfectly optimized. As you can see from the simulated ion implantation of the lithium, this green curve bears no resemblance to what is expected of the lithium distribution in this film. But with proper charge compensation, the SIMS profile now matches the simulated distribution perfectly. So this gives us a confidence that we can actually do these analyses under this setup and move on to the unknown samples. This actually also helps us to get to a bulk insulating sample. It's even more difficult than the thin films. And when we apply the same conditions we've obtained in the thin films, we can find these sodium profiles dropping down sharply and not dragging on deep into the sample. So all these reference materials gives us confidence that we can measure these mobile ions accurately, and we can use that for failure analysis. Why do I say that? I'll give you an example of that in a borophosphate silica glass. And the customer was experiencing in conductivity issues and asked us to do SIMS analysis. And in the SIMS analysis, when there is poor charge compensation, we get a sodium distribution that gives us the impression that when you're growing that film, you're slowly introducing sodium increasing towards the end of the deposition. But this is because of the poor charge compensation. When we apply the proper charge composition, we find that sodium contaminant is actually at the end of the phosphorus dopant. In other words, the spike is introduced when the phosphorus source was shut off, and this spike is right at the interface between where the phosphorus goes down and before the boron goes down. So it is very important that you set up your SIMS instrument to get the proper distribution. Otherwise, you're going to be interpreting the results in an incorrect manner to solve your problem. So let's look at some glasses and see how we can apply these things. For a variety of reasons, glass surfaces require modification for strength, chemical durability, coatability, and looking for impurities coming into these layers, particularly from the substrate and sometimes from the ambient atmosphere. So first example is an ion exchange glass surface, where you basically expose the glass surface into a solution where you get the potassium to diffuse in and the sodium leaching out. And this is commonly done in strength of the surfaces of the glasses. And you almost always need a SIMS analysis to measure the depth of penetration of the potassium and its concentration gradient from the surface from atom percent to parts per million concentrations, as well as the depth of change in the composition in the alkalis. And notice that there has been no change in other elements. One unique capability that SIMS has is the ability to measure hydrogen directly. It is quite useful in cases where you're looking at hydration profiles of float glass, which has a lot of sodium. When these surfaces are exposed to and the hydrogen penetrates into the bulk glass, sodium leaches out, and as well as aluminum. And eventually, this layer will turn into a sol gel-like network, which is less strong than the bulk of the glass. Let's zoom into that area and see what is happening. In this region, which is governed by solvent solution chemistry, the low flow or the no flow condition quickly gets to a saturation, and no exchange is happening. And once that is reached, you end up with a silicon hydroxide groups, and it looks like a low density silica gel, which is not really desirable. And because of the SIMS profile, you can actually see what is happening deeper into the material and what things are happening. At this point, for example, we see the exchange reaction between aluminum and hydrogen has stopped, and the network starts to break down right where this change of aluminum is, and the hydrogen is peaking. And deeper into that is the exchange zone between the sodium and hydrogen, again leaching of the sodium into the solution. Beyond this point, we see that glass network is basically unchanged. Having that tool, this ability to study hydration profiles, we can actually look at and compare multiple samples. These samples, sample 1 through 5, are being exposed to a solution for extended periods of time to study the penetration of the hydrogen or the leaching out of the sodium And because of the nature of the SIMS profile, you can actually measure these layer thicknesses quite accurately and notice what is happening to these elements as the hydration is ongoing in these materials. This ability to measure the hydrogen and the leaching out the elements of the surface became kind of important in pharmaceutical glass vial analyses. For many years now, delamination in glass containers storing the drug solution has been a problem. It is generally accepted that extreme pH conditions react with the glass vial and the surface weakens, and as we saw in the hydration profiles, the sol-gel-like structure starts to form and eventually break off, and these flakes float into the drug solution. Obviously is not a desirable outcome. How does SIMS help with that? Let's look at a glass vial that drug solution is kept. So these are 5 profiles we extracted from this glass vial. We always look at the cross section of a glass. We call it the fracture surface. So we break the glass right around here, turn it on its side, and do a profile at this fracture surface. That gives us a basis for composition to compare with the surface modification of different locations of the vial. So if you look at the fracture surface, we find that all these elements are constant, and more importantly, the sodium, the mobile ion, the difficult element is staying constant all the way to the surface. So now we can use this basis to analyze the other portions of this vial. So the net profile comparison to the fracture surface seems like has very little change in composition, except for some hydrogen penetration, but really the rest of the composition is not changing very much. In the sidewall region, we see that there is some modification, but really it is a very thin layer, maybe 5 to 10 nanometers of layer change. Bottom of the vial shows more of a change, and especially high hydrogen concentration at the bottom of this vial. This may suggest that this vial might have been cleaned during the manufacturing, but stored without perfectly drying it out. So this liquid, the cleaning solution sitting at the bottom, eventually had leached the hydrogen, pushed the hydrogen in, leached the alkalis out. But what we want to focus on is the heel region. We find that the composition of the heel region, which is the corner of the bottom and the sidewall, has the most modification in the surface composition in comparison to the fracture surface, and it has a much thicker change zone. This is the vial that is received as formed. No solution has been put in except for maybe a cleaning solution. And this basically gives us a hint of a trouble spot. So let's look at these areas in an overlay manner. So we're comparing the boron concentration at different part of this vial in comparison to the fracture surface, which is the bulk composition. We can see the bottom, as we were talking about, the hydration had leached the boron out and to the extent where the hydrogen is diffusing in. Same thing is happening for the sodium. And we see that the sidewall is not changed much, maybe a little bit of borate or sodium borate formation at the first 10 nanometers or so. But if you look at the heel portion, however, we see this high concentration of sodium borate forming, and the concentration is deviating from the bulk composition a lot. And over the years, the industry has discovered that this region of the vial is the most crucial part to form the delamination or the flakes into the glass, So many efforts have been put in to understand the flaking off from this corner and how to prevent it. As you can see in the Sims profile of a manufactured glass, we can see these distributions very clearly. What happens if you expose this vial into an acidic solution with a pH of 3 for extended period of time? So let's look at the hydrogen profile in the fracture surface, in the as received sample, and we're looking at the heal location because we know that's the trouble location. So the as received and the fracture surface is similar hydrogen concentrations, and as expected, over time, the penetration of hydrogen has increased. Let's look at the boron. In the as received sample, we have a high boron, but after exposing to the acidic solution, all that boron has diffused out. And the same thing has happened in the sodium. It seems, though, that it comes to a certain saturation, and even after 18 days, you don't see any of additional leaching out. That kind of tells you that the trouble area is actually where the higher concentration of boron and sodium is, and that essentially gives you an idea the thickness of the formation of that weak sol-gel-like structure. And any further time exposed into the acidic solution really doesn't change the amount of depleted region or the sol-gel-like layer structure. So this gives us a help perhaps to use it for predicting the flake size, or whether the formation of the sol-gel-like structures, doing studies similar to this. Now let's move on to coatings of window glasses for architectural purposes or automotive glasses. And these analyses are challenging because they contain these 1 to 2 nanometer layers, which are crucial to the quality of these coatings. They are usually made to increase the refractive index of the window glass, so that during the summertime, the less of the sunlight is coming into the interiors, and in the wintertime, it allows the sunlight to go into the interiors. But the refractive index is controlled by metallic layers, and usually they are silver, chromium, or nickel chromium in the middle of the stack. And they are protected by layers around it, these conductive and transparent layers around these around these metallic layers. And what is needed to know is if the deposition of these layers are following the desired manufacturing, and the thicknesses of these very thin layers. So this chromium layer is expected to be about 2 nanometers to the 3 nanometers. And if whether there's some in the diffusion of these elements or oxidation of the elements, as well as the sodium diffusing out from the soda lime glass substrate into the coatings deposited on top, we can actually see that, for example, this silicon aluminum nitride protective coating on this thing has been deposited in 3 stages, and at every stage there appears to be a growth interruption introducing these oxygen spikes, and it seems like the sodium is actually peaking at these growth interruptions as well, and it is going towards the surface. One thing that happens in these glasses is heating or annealing it to increase the and make it a tempered glass. And the worry when you do the heat treatment of these glasses is what happens to these layers. The reason we are also using the sodium, the SIMS measurement for these profiles is its ability to measure high concentrations of matrices as well as impurity concentrations. As you can see, the sodium is roughly about 0.002 atom percent, and we can clearly see these things. So you have a high dynamic range, you have the depth resolution to be able to identify these layers. So what happens when you anneal that sample? So the same sample, after annealing in 700 degrees C, we see that the sodium from the float glass have diffused all the way, diffused in roughly about 10,000 times into this zinc tin oxide layer. And it actually continued on peaking at this interface and all the way towards the substrate in this protective layer. So we can see by SIMS profiling that the sodium diffusion was immense, and it changes the transparency and the conductivity of the layers. But we see that there's little movement of these layers, the metallic layers in the middle of the stack. In a different example, though, we got a different story. The green curve here is the as deposited film, and the blue curve here is the annealed film. We can see that annealing of this alloy glass coating had the nickel diffuse out even outside the areas where it used to be. So, well, in addition, we see again the sodium diffusing from the substrate into the layers about the substrate. So this kind of SIMS analyses gives us a good depth resolution, good sensitivity to study the effects of annealing in this particular layer structure. But sometimes you have to be careful in interpreting these kind of changes and not being an effect or an artifact of the morphology in this material. So we need to really look at these films with electron microscopy, looking for defects that may give you an impression of these profiles being diffused out, or the roughnesses of the interfaces giving you the impression of the diffused out elements. So it is often necessary that we look at microscopy of these layers in a cross section. This is another low E glass coating. This is a low mag image. You're looking for gross defects. When we zoom into this area, we find that there are some defects that can be seen. This is a Z contrast. So the shades of the darkness is giving you a hint of what the elements are. So the high Z elements like silver is going to be in the lighter color, and the lighter elements like sodium will be in the darker color. When we zoom into that area, we find several different things. We see that around the silver layer, this interface is kind of rough, and we have some growth defects right around here. This is not a perfectly smooth transition. As you can see, there's differences, and then the thickness here is different than the thickness here. So it gives you an idea of the quality of the coating and the interface quality. We see the nickel chrome oxide layer in here, not as clear as we see it in the SIMS, but we can make it out. This is where it's SIMS and TEM combination is very useful because sometimes without doing the SIMS, you may miss out in the low E glass coating analyses this very thin layer. And combining them allows you to hone it into these areas and study what's going on at this interface. We can also see other things. We can look at the topography. This is basically zooming in further into the material. So now we can see the crystallinity of these layers. We see that zinc oxide is mostly crystalline, and the lattice fringes gives you a grain orientation of the zinc oxide layer, and all the other layers appears to be amorphous. And we also see that the roughness at this interface between the zinc oxide and the silver, where we have the nickel chrome oxide, the roughness is of the order of the thickness of the nickel chrome oxide. It makes it very difficult to really study these things. So the combination of the TM and the SIMS is very useful. Now let's look at another technique. While we're doing the SIMS analysis, we notice these speckles on the surface. These craters are the rectangular boxes are the SIMS craters where we did the profiling. And when we zoom in, we see these speckles here. And we need to understand what they are, because these speckles, if they are foreign material, will appear in the SIMS measurement and give you an impression of contaminant when it actually is sitting on the surface. So for that, we usually go to Auger electron spectrometry and to identify what those speckles might be. So these are SEM images at different magnifications in the Auger instrument. These are the SIMS craters. And as we hone in on these shades, we decided to do the analysis right in that circle and try to see what this dark shade is, what this light shade is in comparison to the field area where we don't see any defects. So we identify them as region 1, 2, and 3. When we do the Auger spectrum, after removing the surface hydrocarbon, in the field area where we don't see much of the defects, we see the surface layer of silicon, aluminum, titanium, oxygen, and a little bit of sulfur. So if you look at this area number 3, the spectrum is pretty much similar to the area number 1. It seems like whatever this thing is, it's a buried artifact, not sitting on the surface. But this dark area, on the other hand, we see that it's almost all carbonaceous material, maybe organic, maybe graphitic, but the Auger will not be able to tell us that because it doesn't give you an organic if it is a polymer-like contaminant, as well as other techniques. So what we normally do in cases like this is we do a map, and this is a map of the elements we have detected: carbon, oxygen, titanium, silicon, aluminum. The aluminum and silicon intensities are too low to really pick out in this zone, but we can clearly see where the carbon-rich layers are. The lighter yellowish color is the higher intensity, where the darker red colors are the low intensity. So all these bright spots are pointing out some carbon contamination. When we zoom in and actually look at the area of interest and map out carbon, oxygen, and titanium, we see in this particular case, the green, we see carbon only in this area, not in the field areas anywhere else, not even in this area 3, where even though in SEM and optical image you see something going on there. And outside this area, we see that the layer is mostly titanium and oxygen containing layers. So what we would do is profile into this area, and as we're profiling, we collect spectra from these 3 different locations, and we're going to look at them. This is the profile from the surface. We see that the surface was titanium oxide and silicon oxynitride containing layers, and we then go into a zinc oxide and then nickel layer, silver. Then once we break into the zinc oxide layer below the silver layer, the sample starts to charge up, and we stop the profiling. Now let's look at the spectra of these 3 locations inside the silicon oxynitride. While we're doing the profile, we'll take a collection. We look at the Auger spectrum right here for these 3 locations, and also at the end of the profile at this the silver zinc oxide interface. So let's look at the SiO1 layer first. So we see that this area 2, where it's very dark, we still have this carbon. It's a carbonaceous contaminant. In area 1, we see the silicon, oxygen, nitrogen is expected because we're in the SiO1 layer. Area 3 still shows the same concentration or same signature of the area 1. So it seems like we still haven't reached to what is causing that shade. And the composition throughout the top layer and into SiO1 layer, these 2 spots have the same composition, and this layer is still present and probably thicker than the thickness of the tin oxide, titanium oxide, and the silicon oxynitride. When we look at the area at the end of the profile, at the silver zinc interface, and look at these 3 areas, we see 3 different spectra. So this area, which is the field zone, is giving us the zinc, oxygen, titanium, and silver, as we saw in the depth profile. But in area number 2, which is this plot right here, we don't actually see any of the titanium. So we're still at about the silver layer. We're seeing the silver, but we're mostly in the zinc oxide and the silicon aluminum oxide interface. So this shows that this layer has a particle sitting on the surface, and its thickness is of the order of the thickness of the SiON, and the top titanium oxide. If you look this region, now we finally see a difference. We see that area 1 is different from area 3, where we don't see any of the silver layer, and it's only tin oxide and titanium oxide. So this titanium oxide is below the zinc oxide that is at the interface of the silver. So it gives us a hint that this probably was a void in the silver layer. So and that created that shade. And once we go through that layer, we don't basically see silver anymore, because in that part of the profile, the silver is thinner, or it has a void, and that gives us an idea where the problem might be. And then perhaps the other thing we would do is go in and do a TEM microscopy right at that cross section. So this gives you an idea how you have to combine different techniques to really understand fully what is happening in these coatings. Without really these Auger profiles, you wouldn't be able to really pinpoint where you might want to do a microscopy. If you were to do a microscopy at this cross section, for example, you may not see any of these defects. By doing these analyses with SIMS and Auger, you actually pinpoint where you need to go to do a microscopy to finalize your failure analysis. So in conclusion, I wanted to impress upon you that profiling alkali or mobile ions in bulk insulators like glass requires a very different conditions to get reliable results of these distributions. You have to have a very good electron gun, well controlled, to correct the charge compensations, preventing the mobile ions moving. And we often rely on ion implanted reference materials to justify the true distribution of these mobile ions as we set up our instrumentation for depth profiling. In glasses, we use the fracture surfaces, but sometimes that may not be available for us to do. And again, with the examples of the TEM analyses and the Auger analyses, you often need multiple analytical methods to really fully characterize these glass surfaces and the coatings on glass. I wanted to inform you that we actually looked at the tip of the iceberg today. We just looked at the very top surface of the glasses. We have another glass webinar that's coming up in January 21st, where we're going to look at the bulk properties of these glasses and show you how we do chemical and physical measurements on these. For details, please look at our EAG website. Before I go on to finish the measurement, the webinar, I wanted to acknowledge the colleagues who worked with me on this project: Bob Hengstebek, Charles McGee, Jeff Schallenberger, Jeff Mayer, Pat McEwen, and Mike Salmon. And a final note about EAG. I wanted to let you know why you should actually be using EAG. There are several reasons, but I think it is important to state that most important thing for us is the client confidentiality. It is in the core of our business. We are in full realization of the sensitivity of working with proprietary product, and we have in-house built security systems to protect that confidential information. We are a global leader for materials testing. As you can see, we have laboratories across the globe, and we have 2,500 instruments worldwide. That gives us the ability to have a comprehensive analysis of the materials. So in other words, we don't have a hammer that everything looks like a nail for us. So we choose the proper tool to get the answer for you. And we have scientists like myself and Charles on this webinar that has decades of experience to help you solve your problems.